The first of the factors that affect the takeoff is the effect of mass. Increasing mass has 4 significant effects on the takeoff, all of which can be observed in the formula for the takeoff distance. The first is that a greater amount of mass for a given applied force will reduce the acceleration that the aeroplane can achieve. Essentially, the heavier the object, the harder it is to accelerate it. This is the effect of inertia. More mass will create more inertia. If the acceleration of the aeroplane is reduced, then the distance required for it to reach a specific speed will increase. Therefore, the takeoff distance will increase. A second effect of mass is that there will be more load on the wheels, and therefore wheel drag will increase. An increase in drag will of course reduce the acceleration of the aeroplane. And once again, if the acceleration of the aeroplane is reduced, then the distance required for it to reach a specific speed will increase. Therefore, the takeoff distance will increase. The third effect is not as apparent as the rest. A heavier aircraft will require more lift in order to get airborne. To get this extra lift, the aeroplane will need to travel faster through the air. This means that the aeroplane will need to accelerate to a higher takeoff speed before it can get airborne. Getting to this higher speed will require a greater distance, and therefore the takeoff distance will increase. The fourth effect is that a higher mass will reduce the aeroplane's initial climb angle. This decreased climb angle will increase the distance required to reach the screen height as shown, and therefore will again increase the takeoff distance. The effect that the mass has on the climb will be dealt with more comprehensively in the next lesson. In summary, the effect of increasing mass has 4 detrimental effects on takeoff performance. Always ensure that the aeroplane mass is within the performance limitations. Mass calculations are dealt with more comprehensively in the Mass and Balance course as part of your theoretical knowledge training. The next factor which will affect the takeoff performance is the air density. This has 3 effects. The first effect is that a reduced density means that there is less weight of oxygen available for combustion within the engine. There is also less mass. As a result of less combustion and less mass, the thrust produced by the engine is reduced. Reduced engine thrust will reduce the acceleration force it can produce, and, as a result, the takeoff distance will be increased. The second effect of a reduced density concerns the takeoff speed. You will recall from an earlier lesson that in order to generate sufficient lift, a mass of air needs to flow over the aeroplane wing. If the air density is reduced, then that mass of air is reduced in any given volume. Thus, to generate sufficient lift, the remaining mass must flow faster over the wing. This is achieved by accelerating the aeroplane to a higher speed. To gain this higher speed, the aeroplane will have to travel a greater distance. Therefore, with a reduction in density, the takeoff distance will increase. However, a relationship between the speeds needs to be explained at this point. Dynamic pressure is the force of the flow of air over the aeroplane. You will recall that the flow of air over the wing is exactly what is required to generate lift. This dynamic pressure needs to be maintained to provide the same amount of lift. Therefore, when density falls, in order to maintain the same dynamic pressure and thus the same lift, the speed must be increased. Indicated airspeed works in exactly the same manner as lift, because it too is a function of dynamic pressure. To achieve the same indicated airspeed as the density falls, the true speed must increase. So with the scenario of reduced density in the takeoff, the aeroplane still needs to experience the same dynamic pressure to still generate the same lift and achieve the same indicated airspeed. But now the aeroplane must travel faster through the air to achieve these parameters. Thus we have a relationship in which, when the density falls, to achieve the same indicated airspeed, the true airspeed must be higher. The third effect that density has on the takeoff is that it will reduce the angle of the initial climb, and, as already mentioned, this will increase the distance to get to the screen height. Since aeroplane performance is affected by the air density, it is important to understand and anticipate what conditions lead to changes in air density and thus aeroplane performance. Although the full explanation is outside the scope of this course, high temperatures, high altitudes, and high humidity will all decrease the density of the air, and therefore decrease the takeoff performance. A useful statement to memorize is that high, hot, and humid conditions decrease aircraft performance. The next factor that will affect the takeoff performance is the wind. The aeroplane will always get airborne once a certain value of lift, dynamic pressure, or indicated airspeed is reached. However, if there is a headwind of 20 knots, then a stationary aeroplane will already be experiencing some dynamic pressure, some lift, and an indicated airspeed of 20 knots. In the case of a headwind, then, the aircraft is already closer to its flying speed, and need not travel as fast over the surface to achieve the necessary flow of air over the wing in order to fly. This forward speed over the surface is called the ground speed. Since the aeroplane need only accelerate to a slower speed, it follows that the aeroplane will travel less distance to reach that slower ground speed. So, a headwind will reduce the ground speed for any given indicated airspeed and consequently reduce the takeoff distance. A tailwind will increase your ground speed for any given indicated airspeed, because to get the air to flow rearwards across the wing, the aeroplane must first match the speed of the wind and then move considerably faster than the wind in order to ensure enough lift is generated by the wing. Accelerating to this higher ground speed will increase the takeoff distance. The additional effect that wind will have is on the angle of the initial climb. Headwinds will tend to both increase the angle of initial climb and reduce the takeoff distance, whereas tailwinds will both reduce the angle of the initial climb and increase the takeoff distance. When examining the effects that winds will have on takeoff performance, it is recommended that you do not use the actual wind that is given, just in case that when you do actually get airborne, the wind changes, and thus your takeoff distance changes. The safety recommendation is that the takeoff planning is carried out assuming a worse situation than the one which is forecast. When calculating takeoff distances, it is recommended that you only assume no more than 50% of the headwind component and no less than 150% of the tailwind component. As an example, if the wind were reported to be a 10-knot headwind, only assume 50% of this, which is 5 knots. An important note is that there is no allowance for crosswinds and therefore no safety factor for crosswinds. Crosswinds present an additional complication because of the effect of the potential crossed controls, which would have to be applied when the wind tends to push the aeroplane off the centerline. These issues mean that aeroplanes are given maximum crosswind limits. Most performance graphs that calculate the takeoff distance have the 50% headwind and 150% tailwind recommendations already applied. The example shown here includes this. You will notice this recommendation because of the different slopes of the headwind and tailwind lines. Tailwinds have a greater effect on the distance than headwinds. This can also be seen on other graphs by looking at the scale of the headwinds and tailwinds rather than just looking at the slope.